Hi, today we are talking about the effect of various parameters in flash cut foreground extraction with flash and non-flash pairs. And let's just start. So to tell where the story began, we are trying to solve a problem where like in a picture, you have some object that is close to your camera and the other parts are very far from the camera. So we kind of want the extension like the foreground and the background. So the foreground is closer to our camera and the background is part of the camera. And we want to like classify which parts are the foreground and which part are the background. So this is our problem. And what do we need? So like in the previous papers, the methods typically require some like motion vectors or like stereo or infrared light, which you all have like this kind of additional information from either camera or other settings. So, but it turns out, okay, there are only two images we needed to solve this kind of problem. And one is the flash image and the other is the non-flash image, which is pretty simple. And how is that possible? So we need our output or our like goal is to have a binary matrix of 0 and 1, which 0 represents like that pixel belongs to the background and 1 represents that pixel belongs to the foreground. So let us call it variable xp. So how do we solve with the general principle with the flash and non-flash pair is the foreground object will have been much more heavily affected by the flash compared to the background, which only have minor influence on the camera, on in the images. So in our solution, we just want to minimize the energy of a Markov random field. So you don't have to know of that what that is. It is simply like we try to minimize the set of energy. If we like if we give some kind of classification for each pixel, we got like either penalized or not penalized for some cracked or almost correct classification. So you can see there's two terms here. One is the EDXP on the left, and another is the like 2D relations. So we skip the second part, which penalize if we classify two adjacent pixels with different labels, but they actually have, they are very similar in the intensity. And all the terms we're describing here are only using one simple channel, which is the intensity channel that is like the grayscale convert from the RGB values from the original pictures. So we only consider the first term, which is the EDXP term. And the EDXP term is some weighted factor, the gamma F, gamma M times the EF energy, the EM energy, and the color term. And we also skip the color term because we kind of run out of time. And how do we compute the foreground term? Okay, so the general idea of the foreground term is first, you classify those intensity into a lot of histograms. Since we have really big pictures, like 6,000 times 4,000 pixels values, we simply just use the 255, like all 256 histograms and put them into the boxes. And the flash ratio is simply for a certain pixel and the corresponding, the different classification, the intensity bin of flash pairs and non-flash pairs accordingly. What's a count difference? Like there may be like 300 pixels in the flash and only 50 pixels in the non-flash of that pixel bins. And how many percentage change compared to the original count is the definition of the flash ratio. And the final foreground term, if we classify it as a foreground, so xp equals to 1, we have to there is some like punishment, the energy value we have for the ratio. And if there is just like background, then this is just 0. So the higher the flash ratio, the most likely, remember, the foreground term represents how much the effect on the part that has been more heavily affected by the flash. So, and the robust parameter 0.2 is just kind of setting a threshold. If it's like above 0.2, then you actually count for the energy. And the background term is much more simple in my understanding. So we have the motion vector computed based on the flash and non-flash pairs. And there's a method for the dense feature that you guys don't have to know. So basically, we have the corresponding p prime pixel in the flash image minus subtract from the original non-flash image, and we want the difference of that image. And the background probability is the distribution of the ID is mu and sigma b. And this is basically the probability term is like the Gaussian function. And then we kind of normalize the probability into 0 and 1 and compute the background term. And this is how we like kind of estimate the mu and sigma. So we simply find the mu and probably like see from the graph how much deviate from the first local either local being or anything like that. So this is our like original pictures, and the final result you can see the result is pretty decent, except maybe in the non-flash part there are some like backgrounds that are misclassified as a foreground, but it's fine. And here is how we change some parameters and how does the result change. And this is the contrast parameter, like how much difference between like the contrast parameter is like you multiply this parameter on the image and clip it from 0 to 1, which kind of increase the difference between various parts of the image. And we can see there is basically no changes besides like some of the background got a little bit misclassified. And the sigma parameter is, remember, just like back a few slides ago, the sigma is the deviation, standard deviation for the distribution of the IDF, the diff matrix. So we can see, so the left, right, the left top is 0.25, and it's just increasing from here, from left to right, and from this one is the largest sigma value. This one is the smallest sigma value. We can see as the sigma increase, we got more background. We got less misclassified of the background. You can see a lot of background is classified as a foreground here, but we also got less foreground stuff getting classified correctly. You can see like my face is tinted with background stuff. And this is the gamma f term that is like the weight you put in front of the two energy term there. So this one is 1 to 2, so more from the background term, and this one is more from the foreground term. We can see like this one, the top one is simply the best because it basically not misclassify anything, while the bottom like misclassify a lot of background stuff. So our conclusion is, among all parameters, the different standard deviation sigma is the most important factor in our analysis. And as a side result, sigma is probably the most ideal candidate for implement continuous distinction in the future. So it's not just like either background or foreground. It can be like, we want more background and we want more foreground, that kind of stuff. So, and another conclusion is like a lot of factors are not thoroughly examined, like the dark light, the low ISO sighting, and we have a lot of changes, implementations from the original paper. So, and we might take improvements in the future accordingly. And this is basically all the presentation. Thank you, guys.